Hi everyone, so this is the third part of the video. We have discussed what is Schrodinger's wave function. Then we had dissected what is Schrodinger's equation. And now the part which is there in our syllabus, that is the solution of Schrodinger's equation such that we get the shape of the orbitals in which the electrons are, and then where they are not, that is the nodes and all. So that's the part which is mainly in the syllabus and not how to solve it, but then we should be knowing what is the equation, and hence we discuss that. So carrying forward from where we left, so I had given you the Schrodinger's equation. Now if you look on the screen, this is that equation, and what you are finding over here is I have written the equation now in polar coordinates. What are polar coordinates? It was told earlier also. I'll just repeat. Instead of x comma y comma z, we are writing in terms of r, theta and phi. So we are writing in terms of the distance of the point from the origin, that is your r, then how much angle it makes with the z-axis, that is your theta. So what would be the projection of the point on the xy plane? That's your x and that's your y. What will be the projection? What will be this line? Will it be r cos theta or r sin theta? This will be equal to this, which is r sin theta. So this guy over here is r sin theta. That's the line over there. So what is y? What do you get your y as? You'll get your y as r sin theta sin phi, and x as r sin theta cos phi. Shall I write it or just leave it? R sin theta, this is your r sin theta, that's the hypotenuse of this right angle triangle. So you have cos phi over there. So instead of x, y, z, and instead of writing partial double differentiation of our psi function with x, we are differentiating with respect to, you can see over here as r, with respect to theta and with respect to phi. So it's the same function written in r, theta and phi, so that we can have the radial part separated out from the angular part. So if you write the function, what was this? This totally was your Hamilton operator, of which this was your kinetic energy part. This was what there was. You will see another difference over here. Instead of m, I have written a mu. Why is that? That's the reduced mass of the system. I have to write the mass. That's the reduced mass. Mu is the reduced mass of the, so mass of the electron times mass of the proton upon mass of electron plus mass of proton. So anyways, you'll be doing reduced mass in when we'll do SHM and all later on in physics. So you don't have to worry. You just have to know that you have written a kind of combination of protons mass and electrons mass. Because in the system you have a proton and electron, and this potential is due to both of them. It is not like one is producing the potential energy is due to the presence of both. So this is the potential energy particularly for the hydrogen atom. So this equation, this Schrodinger equation has been written for hydrogen atom particularly. I'll just clear it up a bit. So the thing is, we want to separate out, we want to write this function, the wave function, as two parts, as function of r and as function of angle separately. So thankfully it is possible mathematically by ways of separation which you don't know yet, which we don't have to know. So the point what we have to know is this wave function has been separated out in two parts. One is the radial part and one is the angular part. This is your radial part and that's your angular part. Now if it is separated out in angular and radial part, we'll substitute these values over here. We'll do some math. We'll say that phi itself was of two parts, radial and angular. That's your r and y. They're not writing the whole thing over here. So if you are differentiating with respect to r, then y becomes a constant, y goes outside, and you're differentiating r. Similarly, if you are differentiating with respect to theta, then r will go outside and y will get differentiated when we are differentiating with respect to theta and psi. So when you do that, this will be the function. You can have a look at it later on. Doesn't matter much. So your ry is in fact your psi. The wave function what was is your ry, where r is independent of angles and y is independent of radius. Y is only having the angles in it and r is only having the radius in it. In r, radius is what is varying, the angle is not varying, both the angles are not varying, and in y, the radius is not varying, it is for a particular radius. So this has been successfully separated out as two parts. This is one part and that is the other part. So what you need to know is that the wave function has been written in polar coordinates, which is r, theta and phi. It has been written in this form instead of xyz form, and it has been successfully separated out in two parts. One is radial and one is y. So hereafter, whenever you see a graph of phi, most probably we would be making a graph of r, this r. The wave function will be the radial wave function only. What we'll be talking about is the radial wave function. So don't think that this r is radius. This r is not radius. That r is the distance from the nucleus. The small r is the distance from the nucleus. This r is the function. We have replaced this with that. Whenever we are not going to make graph of y, that's the angular part of the wave function. We are not going to make a graph of this because that will require a 3D space, in fact a 4D space to make all the graphs. You have three variables over here. A 3D graph requires 4D. I hope you know a 1D graph requires a 2D plane to draw it. If you used to draw x versus time over here, this was a motion in 1D, right? It was a motion in 1D which is drawn in 2D. So 3D will require 4D. We don't have to do that. We are just going to draw 2D graphs, which we'll come to later on. But the thing is, what we want to know right now over here is, instead of wave function, we'll be referring to this radial wave function, the radial component of the wave function, which is this. It has been separated out in two parts. So this is equal to the real parts will be equated to real part, imaginary part will be equated to imaginary part, and you will get a certain solution. So from this page, what you have to take home is that the Schrodinger's wave function has been broken in two parts, radial and angular, and the radial wave function is what we are going to study further. Okay, now solving Schrodinger equation, what do we get? We get energy. That is one of the results of solving the Schrodinger equation. I'll give you a YouTube link of how big fat solution it is, and a website URL also. You don't have to actually watch it. If you are just curious, you can see what they do to solve it. It will involve a lot of math which you have not heard of. So you'll get energy on solving, and you'll get the wave function itself on solving. Now the wave function which comes will have n, l, m in it. It will have the quantum numbers in it, and the energy, surprisingly, the energy which comes is having only one integral numbers in which it jumps, and that is n. Only n is what is coming. While when you solve energy, you don't have a m in it, you don't have a l in it. So only on the principal quantum number does the energy depend. What does it mean? It means, like all orbitals of one has only one orbital, or orbitals of 2, all orbitals of 3 will have the same energy. When n is equal to 1, 2, 3, whether it is 2s or a 2p, whether it is a 3s or a 3p or a 3d, all have the same energy. So if I make a diagram, that's your 1s, that's your 2s and 2p at the same level, 3s, 3p, 3d at the same level. So we say these are degenerate energy levels. So the Schrodinger equation gives us that they are at the same energy. By the way, the Schrodinger equation doesn't take care of the spin of the electrons. So the spin was not known when the Schrodinger equation came, and when you take care of the spin of the electrons and the other factor, that is your mass, you take the relativity into account, and using relativity, if you correct your mass over here and take the spin into account, there is another equation which is a more what can I say, a deeper solution of the atomic structure, which is Dirac equation, which you don't have to know at all. So it takes care of it in fact gives that 2p is not having the same energy as 2s, even when there is no external magnetic effect. If there is external magnetic effect, by the way, these degenerate orbitals, they go at different levels, meaning to say this 2p will rise up over here, this 3p will rise up over here, 3d will rise up over there. So there they will split up. They will split up into the energy in presence of external magnetic field, which is called Zeeman effect. So that is a kind of shortcoming of Schrodinger's equation, but it is a good basis of things to follow, and gives you pretty accurate model of the atom. In fact, the energies of this 2p and 2s is, or 3d is very slightly different from 3d is very slightly different from a 3p orbital. Okay, so I hope you have gathered enough information till now. So what else apart from the energy what I showed, what else do we get? This was your energy. What else do we get? Mind you, this energy, if you remember, when we were solving Bohr, using the fact that the electron has attraction towards the nucleus with a force of F is equal to kZe square by r square, that was a force. Your centripetal force, this was put equal to centripetal force mv square by r, and then we had taken the Bohr's postulate, that is mvr is equal to nh by 2 pi. Solving these two, we got the potential energy and kinetic energy. Here k is 1 by 4 pi epsilon naught, and we got the total energy somewhat like minus 2 pi m e power 4 z square divided by there was a k square, our k, this k, and n square h square. If you work it back, if you replace the k with 1 by 4 pi epsilon naught, you'll get exactly this thing. So in fact, Bohr's solution, where he guessed this from is another thing of discussion, but I mean, he imagined it pretty well, that the angular momentum is in quantums, it has jumps of h by 2 pi. So using that, we are at least getting the energy of the Bohr model, and energies by Schrodinger, same, of the principal quantum numbers. Now what Bohr said are the shells, are the orbits, are they the shells? That we'll have to see. At least the energy what Bohr calculated is same as the energy getting calculated from the Schrodinger's equation for a hydrogen atom. for a hydrogen like atom, if I can say. Now we'll come to this a bit later also, but you can have a look. What we are having over here is these are the outcomes, the solutions of your wave function psi. As has been told earlier, the Schrodinger's equation will give you several solutions depending on the quantum number. So it has got these numbers you can fit in. N is your principal quantum number, L is your azimuthal or angular momentum quantum number, and M is your magnetic quantum number. So N basically is telling you the energy. Straight away you are seeing from the energy equation, it is telling you the energy level. L is giving you the shape of the orbital. It is telling you the angular momentum of the electron, and in 3D it is also giving you the shape of the orbital. M is telling you information about the magnetic effect of the electrons in there, and it is giving you the orientation of the orbitals. So that is what M is giving you. So we'll have a quick look on L, M and N again, but what I want to emphasize over here is the wave function what we are getting. You see this kind of wave function. In my previous video I was trying to differentiate a e power minus omega t to show you that a double differentiation will give you roughly the same thing. And in a later video, I think I have edited that, we showed you how e power ikx will get the negative what we wanted in front. So how that can come. So anyways, so if you look at this function, this is the complete function with all the ingredients in it, that is theta, phi and r, and this is where it has been split up in. This is your angular part and that's your radial part. So we'll be more concerned with the radial part. So you can see that r, instead of most often this y axis, even if they are writing the wave function, they are mostly meaning this r, that radial component of the wave function, rr. So it has been plotted by rr and not psi. So you see this is having a constant in front and e power minus r something. So if you plot against r, this axis is r is the distance from the nucleus, you'll get a minus e power x kind of plot. Y is equal to e power minus x kind of plot. E power minus x, that is this. I hope everybody knows that. E power minus x, you have your e power x graph which goes like this. So e power minus x is a reflection of that. You'll be doing in basic maths if you haven't done yet, and there is no meaning of negative radius, so we'll just curtail that part and it comes like this. So this kind of graph and variations on that creates the radial function of radial wave function. So you can see that it is never going to touch 0. X may be a very high value, e power minus 100 will be almost 0 but not 0. So this goes on and never touches the x-axis, by the way, it keeps on going like that. So that's your 1s. How does it depict the orbital? We'll come to that later, but this is the graph of 1s. What do you mean by 1s? They have given letters to it. These are going to become orbitals. That is a story of later on. 1s means n is equal to 1 and l is equal to 1. In the solution what they got, in the big fat solution, I just did not write that solution. That solution I could have printed over here. In that solution you'll put your n as 1, l as 0, and you're going to get this as the graph. Your r is only going to depend on n and l. R is only going to depend on that. So when you have a 2s function, what do you see? You'll have some constant in front of it and you have this kind of graph. This means what? 1 minus r, that is, this can become 0 now. This thing can become 0. When will it become 0? When your r is 2a. When your r is equal to 2a naught. What is a naught over here? I hope you remember that. A naught is what came as Bohr's radius, which was 0.529 angstroms, right? It's like around 53 nanometers. That's I think written over here. 0.0529, sorry, 53 picometers. I'm so sorry. That is 0.529 angstroms, which is 0.0529 nanometers, 53 picometers. So that's your Bohr's radius, first Bohr's radius. That is your A naught. That's your A naught. So if R is 2A naught, this function will become 0, right? So this point will be, that's this function. This one has been 2s has been drawn over here. This point is R is equal to 2A naught. So these kind of questions may come. They'll give you that this is the wave equation, and they'll ask you when is it becoming 0. Now when it becomes 0, it is called a certain thing. When we draw the orbital, we'll know that it is called as a node. We'll see that a bit later. So they'll not give you this and say when is it becoming 0. They'll ask you where is the node, So it is as good as asking where is this guy becoming 0. This guy is becoming 0. You don't have to bother about this. This will never become 0. It's a constant. You don't have to bother about this. This will never become 0, and this is going to become 0. So when it becomes 0, that's your node, and then you will say that okay, this is my node. So we'll come to that a bit later. So we are just examining the wave function. You see 2p is quite different from 1s and 2s. 1s and 2s at the x-axis at r is equal to 0, it was going quite high. The wave function was going quite high at r is equal to 0. At r is equal to 0, you'll put r is equal to 0 over here. E power 0 means 1. It is going to touch the y-axis, which is your rr. That's the radial function. That will become 2 divided by a naught whole power 3 by 2. So in p, what is the difference between, now that you should be knowing, because they will ask you to identify what is the difference between 1s, 2s and 2p radial wave function graphs. What is the difference? The difference is 2p starts with a 0. It starts with a 0. The others are starting with high value. 2p starts with a 0. It starts with a 0 because if I go into the 2p graph, we have a r in front of it. When r is 0, what will happen to this function? When r is 0, the whole function will be 0. So r is equal to 0, it is 0. For p, for electrons which are going to be of the p kind, that is it is going to be living in that p orbital, those are never going to be at the nucleus. We'll see that. In fact, these are also not going to be at the nucleus, but these are not going to be at the nucleus not because of the wave function going low or the probability density going low. Wave function will ultimately mean probability density, which we have discussed. They will be not at the nucleus because of other reasons. We'll discuss that reason in a while, because of two reasons. But this p, an electron which is in p, will never be at the nucleus just because there is no probability density at the nucleus for those electrons. The probability density is mostly here and here. It is not at the nucleus. But for an S which is around, which we'll see, there is a big probability density of it being at the nucleus. Then why it is not at the nucleus, we'll look into that. I hope you have understood that if the radial wave function is given, it is not a big deal to figure out where it is 0. It is not a big deal to figure out where it is 0. R0 will make that 0. 2 minus r by a 0 will make this guy 0. Right? It is not a big deal to figure out that thing. Okay. Sometimes when they are too much into math, they can ask you where it is the highest, and particularly not in this one, in the square of this one. How do you get that? That is by differentiating and finding the slope. So that will do much later. So I don't want to divert from our main thing. The main thing is we got energy from there and we got wave function. Energy came only in n's, no L in it, no m in it. Wave function came with a lot of n's and l's and m's in it. N, L, M. When you put those n, L, M values in the wave function, these are the wave functions. These are the look of the wave functions. They look like this. Let us see the third shell also. The third shell is having L from 1, 0, 1 till 2, right? 0 will have only 1m. This one guy will have 3 m's, a 0 and -1 and +1. This two guy, L is equal to 2, which means D, L is equal to 2, which means D will have 5 m's, m0, and then from -2 to +2. The 0 over here, mind you, the 0 over here is associated with Z. So if I am writing for 2p and a 0, it is for 3p and a 0, it is 3pz. 3d with a 0, this is 3, this is d. 3d, 0 is conventionally for z, so it is a z square. So z square. The other ones are your xy's and your y square x squares, your yz's. So we'll see those shapes. So what we want to have a look at is when this wave function is separated out, this is the combined one, and graphing the combined one is virtually impossible because we need 3 variables changing over there. We need a 4D space to do that. So we are not going to study that. What we are going to study is when this combined one is split in 3 parts. These 2 parts are the angular parts. The angular part which I showed you in the first frame is further split into 2 angular parts. One when the theta is varying and psi is not varying, and then phi is not varying, and then when phi is varying and theta is not varying, and the radial part when both of them are not varying. These 2 are not varying and only the radius is varying. So this part, what is this giving? It's giving a quadratic over here. That means this function can become 0 how many times? 2 times. Let me just see. 3 0 0, meaning to say 3s. Is it becoming 0 2 times? Yes, it is. Here and here. If asked to calculate, will you be able to calculate? Yes, you would. And that would be like advanced question. That would be an advanced question. Putting this equal to 0. It's quite cheap. Your quadratic equation equal to 0 you used to put in class 10 and class 9 to get the answer. Now they are giving a big fat equation and asking you where it is 0. Basically they are asking the same quadratic equation from you what you used to do. So the variable is r over here. So it is just understanding of the equation which brings in the fear and makes it a higher standard question, but as such there is no difficulty in solving it. Now what is this? 3 1 and 0. That means the third shell we are talking about p. So it is 3p. 3p is a linear over here. That means it has got only one 0 value. Looking at this, that 0 value is at 6a0. When r is equal to 6 times a0, a0 was the first Bohr orbit. So 6 times that comes to be the node of p, and we'll be seeing that. So we'll just say in terms of makes it 0 right now. So it makes this 0, makes that 0. Do you expect any difference with 3pz? That is your z and that's your x, and 3py, these are x and y's. Do you see any difference over here? Not at all. We don't expect any difference in that. So your radial function for 3D, whichever, all 5 will be same. Are they same? Yes, they are same. The radial function is same for all of them. The radial probability distribution will also come same for all of them. So these are the wave functions for 3D. If a question comes, they'll be throwing one of these wave function and they'll be asking you something. If you have to solve for any of these equal to 0, I don't think it's a big problem. This thing can never become 0. This thing can never become 0. This thing cannot. So these things cannot become 0. This guy e power something can never become 0. That thing can never become 0. So what can become 0 is this quadratic. This is a linear into r by a. So the other root, mind you, the other 0 was, I said linear, and there is r also, so I just forgot to mention the other 0 is at the nucleus, and nucleus we don't call it as a node. So the node will be this one, we'll discuss that node. So at r is equal to 0, it is 0. So that 2 0, this is a quadratic in fact fully. This is also a quadratic. This is also a quadratic. This is also quadratic, but both the zeros at the nucleus, which is not called as a node. That's your r square is equal to 0, meaning to say r is having zeros at 0. Okay. I hope you have understood this. If you have any doubt, you keep noting your doubt so that when I take a live lecture, you can ask those things frame by frame. You note your doubt, that what's your doubt in the first frame, second frame and third frame. Mostly first frame, whatever has been said will not matter much. Those equations won't matter much, but the fact that this was being broken, the angular and the radial part will matter. That's the only thing what is going to matter. Okay, so let us go on to the next frame. Yeah, so I showed you the wave functions, and in those wave functions we had n, l, m. You replace the n and a l and a m in those wave function, then you'll get a certain graph. So we had shown, we had discussed the various, just shown the various graphs in a glimpse. We are going to do that in detail, obviously. So the L, N and M, what were those meaning? What was the meaning of that? So this N is very closely corresponding to what N meant in Bohr's model. N was the orbit. Here N is the energy level. So N has a similar interpretation. It is the principal shell. It means the shell N1, 2, 3, 4. These will have subshells. So this has just one subshell, which is 1s. This has S and a P. This guy has got S as well as P as well as D. This one has S, P, D, F. And the next one will have S, P, D, F, G, if at all G is required to be filled up, but it has those subshells. So mathematically all those possibilities are there. So these N is principal shell, which is containing all those. So if I take this one, this will be too much to draw. I'll take that one. So that's your principal shell. You'll talk about a region of a certain radius. In that you have this S. S is, mind you, going to come as more than one spheres. What you expected as just one sphere is going to come as more than one sphere. This P is going to come as other beautiful shapes, and D is also going to come as some dumbbell shape kind of thing. So in this region, all of them are confined, and this region, all these orbitals, which we will be calling them as these as subshells, and the doublets of electrons where they reside as orbitals. So these S, P, D, all of them will have the same energy. So the principal shell has got subshells which have the same energy in a hydrogen-like atom. In a hydrogen-like atom, the solution of energy is having only the N in it. So the principal quantum number N corresponds to N used by Bohr. First radius corresponds fully, by the way, with the first shell, because it is having just one kind in it, and which is S. The other one is a bit complicated. It has two kinds of shapes in it, and there the radius doesn't correspond. Should it correspond to S or P? It doesn't correspond. We'll see that in a bit of time. But it is mostly what Rydberg said, the atomic energy levels. So Bohr called those N's as the orbits, the radius of the orbit. It is, those N's were depicting that, and Rydberg had depicted them as energy levels. So this is more of energy level. The quantum atomic number is now shells, which in hydrogen atom are energy levels. I hope you get that. Yeah, okay, now the next quantum number, which is azimuthal quantum number or the angular momentum quantum number, because the value of this quantum number, which is L, that changes the angular momentum, that tells you the angular momentum. For L is equal to 0, it's a certain angular momentum, and for L is equal to 1, it's a different, altogether different angular momentum. So the angular momentum is jumping in quantums, so it is quantized. The angular momentum itself is quantized, and that idea had come before to Bohr. In this, the solution of the Schrodinger is automatically depicting that the angular momentum has to be quantized for, as I said earlier, for the solution to happen, which is like standing wave to happen, so that the electrons don't cancel each other out. So that is the basic criteria on which the equation has been written. So yes, your L will go from 0 till n minus 1, meaning to say if your principal shell number is say 5, then L is going to be 0, 1, 2, 3, 4 till 4. 0, L0 will be given a name, and that is S. These names are short forms of your spectroscopy, what terms are used over there. So S is, I guess, for sharp, and then P is for principal, SPD, I think diffused, SPD, F is fundamental. So your shell number 5 will have a G, technically G also in it. After F, the elements are not enough that you will fill up everything. So after this, it is just F, G, H. Now, so what are these called? These are called subshells. These are called subshells. These SPDFs are called subshells. So subshells are having further divisions, and those are called orbitals. So certain subshell has got orbitals, and we have discussed that in the live class earlier, right? So we don't have to emphasize that. So a S subshell is just having one orbital, which is the S orbital, and it is not having any other orientations. But a P or a D or a F, these subshells have orbitals which can be oriented differently in space, and that orientation is given by the magnetic quantum number. So I hope you understand that if you change the magnetic quantum number, it is not going to change the energy at all. Even if you were guessing that L should have some effect on the energy, L was a different shape altogether. Your L0 is this, and L1 is this shape. So you might have thought that it will have some effect on the energy. It was not having for hydrogen atom, but M cannot have any effect on the energy, because M is simply saying that one of the L's, one of the orbital in the P subshell, that L means P subshell, is like this. The other one is oriented that way, and another one is there which is oriented in and out. It is just telling you the orientation. So it is absolutely, all of them are absolutely symmetric. So no question of either change in angular momentum or energy. Whatever angular momentum will be of this is the same for that. Angular momentum for an S was not equal to L for a S. Angular momentum for a S was not equal to angular momentum for a P. Hence the number itself are not equal. This is a 0 and that's a 1. Obviously we know that 1 is not equal to 0, because that L value is ultimately giving you the angular momentum. How much it gives? The angular momentum given by L is equal to L into L plus 1 h bar. That's the angular momentum given by L. So obviously if L is 0, then your angular momentum is 0 into 0 plus 1, which is 1 under root h bar. If L is equal to 1, then the angular momentum is 1 into 2, that is root 2 h bar. 1 h bar for S, root 2 h bar. And then if L is equal to 2, which is for a D L is equal to 2, the angular momentum is 2 into 3, that is root 6 h bar, where h bar is your h by 2 pi. So that changes the angular momentum, but obviously the angular momentum will not change if the orientation has changed. So it doesn't change the orientation. So what does physically depict? M physically, one is it is showing the orientation, the effect. What is the effect of it? It gives different magnetic effect. So in very layman terms, if you have a magnet like this and if you have a magnet like this, obviously they'll have two different magnetic effect on the environment around it, right? So it is having different magnetic effects. So that's called your magnetic quantum number, and these are the only three quantum numbers which are involved in the Schrodinger's equation. S spin is not there in Schrodinger's equation. Okay, so let us go on to the next frame. So what we see is M, which is the orientation of a L subshell. The total number of orientations can be, if L is, say, L is equal to 1, the orientations are 0, -1 and +1. If L is equal to, say, 2, the orientations are 0, -1, +1, -2 and +2. So what we are seeing is that the total number of orientations can be 2L plus 1. If L is equal to 0, which means S, twice into 0 plus 1, which is only one orientation, which is just the sphere. But if L is equal to 1, 2 into 1, which is 2, plus 1, which is 3 orientations are there. It is going from -L to +L. So many orientations are there. So we'll see the orientations, how they are oriented, how these orbitals are oriented. So a certain subshell has got orbitals which has so many orientations in it. So a certain subshell which is depicted by L is having 2L plus 1 orientations in it. So we'll just see how many orbitals can be there in a certain shell. So just pause the video and fill it up how many orbitals in a shell can be there. So if we are talking about this shell number 3, it has got subshell 0, which is S, subshell 1, subshell 2, which is a P and a D, and these will have how many orbitals? 0 will have 1 orbital in it, that is S will have 1 orbital in it, P will have 3 orbitals in it, D will have 5 orbitals in it. So 1, 3 and 5. If we had one more subshell, it would have 7 orbitals in it. So 1, 3 and 5 and a 7 for the next one. So what you see is it is going up in odd numbers. So the number of orbitals are just the odd numbers added. So 1 plus 3 plus 5. So what will that be? 1 plus 3, 2 things added is a 4, which is 2 square. 1 plus 3 plus 5, which is 3 things added, 3 odd numbers, consecutive odd numbers added, which is a 3 square. 1 plus 3 plus 5 is 9, is a 3 square. So we are seeing that it is square of the shell number. It is square of the shell number. It is n square, right? So in math you would have derived it. You can derive it by induction also, and you can derive it by just by series or summation also, that if odd numbers are added, in fact you have done AP last year, apply your AP over here. If you are going from 1 to 7 and there's a jump of 2, then what is the total of it? First number plus the last number by 2 is the average. This plus this plus this by 2 is the average into the number of terms, which is 4. And what is that? So you'll have 8 into 2, which is 16, which is again n square, 4 square. This is your 3 square, which is 9. That's your 4 square, which is 16. So if you add up odd numbers, it is just the square of it. Instead of 1 and 7, you can plug in the odd numbers, say 1 plus. So if you want to get that general formula n square, what you can say is first term plus last term. Last term will be what? If the shell number is n, then the last term will be 2n minus 1. You can check out with this. 3 twice of 3 minus 1 is 5. Twice of 4 minus 1 is 7. 2n minus 1 is in the format of odd because 2n is even. First term plus last term by 2, that is the average of terms, into the number of terms, which will be n itself. 1, 2, 3, 4, n itself. So you'll get that. So what you get on top is 2n minus 1 plus 1. So it is a 2n in fact. 2n by 2 is 2, 2 gets cancelled, n itself, and n into n is n square. So that is how you can derive it if you want. So just wanting to you be comfortable with all the number of orbitals present in a shell. So you see this shell is having 16 orbitals in it, 16 orbitals in it, 16 orbitals in it. That's a and 16 orbitals meaning to say what? How many electrons can reside? 32 electrons in each orbital. 2 electron can reside. So it's a big fat shell, and it should be, because if you remember Bohr's radius, it grows in n squares. So the first radius is whatever, the next radius is 2 square, 4 times that, and the next radius is 9 times that. So in fact these are, as we were talking about shell number 4, n is equal to 4, shell 4. What we have got? We have got a s, we have got a 4s in it, we have got 4p, z, there's a x, there's a z, there's a y. Z is necessarily the when m is equal to 0, we associate it with z. Here also z square will be m equal to 0. So these are your p's, 4 p's, 3 of them, and then you have the d's, 4 d's, 5 of them. These are all d's, and the name are xy, xz, z square. Z square I'll call it as m equal to 0, because this is the odd one out. The odd one out is along the z axis. So whatever happens which is odd between them, like if they have to approach another atom, so it has to approach by one axis, we'll take that axis as z axis by convention. So these are your d's, yz, and your x square, y square. So xy is in the plane of xy, that's your z. You have your xy plane. In that plane, that's your y, that's your x. In that plane, if the orbital is there, not going up, not going down, in that plane if the orbital is there, it's called xy. Similarly, xz, if it is in the plane of x and z and not going in the y direction at all. If it is totally in the z direction, that's your z square. Now this is your yz, so it doesn't have to go in the x direction at all. It has to be in the plane created by your y and z. It has to be in that plane. So it is in that plane. And this one is your x square, y square. So again in the xy plane, but not along the midway of x and y axis, which is 45 degrees to x and y, not there. That was your xy, but it is along the x axis and along the y axis, and the name is x square dash y square. It's along x axis and y axis. Z square was along z axis, but then you have to give almost equal volume kind of thing to them. You have to give the equal volumes so to compensate. Everything is having 2 lobes, z square is having just 1 lobe. To compensate for that, you have a ring around it. That ring is in the xy plane. So that's 5 of the d's, and then you have 7 of the f's. The f's looks like a triple lobe. That's your f. It is same as we had discussed in the class, growing up like a flower. So again you can manage triple lobes, but then you'll have one odd one out. So we'll have this as the central one. When m is going from -3 to +3, the 0th one will be called your fz cube. So it is having 3 in it, so it is called z cube, fz cube. So that's a pretty shape. So the f is never going to be asked, so don't have to worry about it. What you should know is the shapes of s, p and d. So s and p for sure is the favorite among questions, and sometimes d is quizzed. These are the orbitals, what we are going to get from the wave function graphs. So how do we go get that? We'll go on to that next. Okay, now this is quite important to understand. What we have seen till now is we have seen this graph, radial function, radial wave function versus radius. That's the graph we have seen for 1s, 2s. So it was shown to you earlier that that's the graph. Now this radial wave function or the wave function itself doesn't give you the probability which we have discussed earlier. It is given by the square of the radial wave function. So if you square the wave function, in fact it is given by the wave function itself is a complex number. So if you multiply with the conjugate of the complex number, if you multiply with the conjugate, then you are going to get the square of the magnitude, square of the how much of amplitude it is depicting, and that gives you the probability density as figured out by Max Born after Schrodinger came up with the equation and he could not give an explanation of what can this psi mean. Then a psi square, we'll call it, it is in fact a multiplication of the psi with its conjugate. So any imaginary number you'll be doing in complex number in the next month, when you multiply imaginary number a plus ib with its conjugate, which is a minus ib, what you get is a square plus b square is what you get, and a square plus b square under root is the effective length of the vector or the magnitude of it. So a square plus b square without the under root, the square. So that gives you the probability density. Meaning to say, if you have a high probability density means if you are talking of a certain volume, if you are talking about a certain volume, you multiply the probability density with that volume. So that probability density, if it is multiplied with a volume, and assumingly it's the same probability density in the whole of volume, that gives you the probability. So your probability is not your phi square. So there are three graphs involved right now. You'll see one is the psi, which is the function itself. They are writing r because it's the radial part of the function, and angular part we are not doing, as we said earlier. The other one is your psi square, that gives you the probability density. And the third graph is volume. The graph itself will give you the volume. This is not the volume, I'll just explain what it is. So the third graph is what I'm trying to explain over here. Now what is probability density? You are seeing that the probability density when your r is equal to 0 is quite high. What does it mean? At nucleus the probability density is very high, and you can see if this is your watch over here, if this is your atom and the central part is your nucleus, then if the density is depicted by putting some sand grains, these dots, you can assume them as sand grain. So more of them are put, more of the dots are put, it means that it is high probability density, and less are put, like here it is spaced out, it is low probability density. Let me give you a figure. I think I would be here, like this is a probability density spotted like this. This area is having a lot of dots, it is high probability density. Then this one is low probability density, here it is low probability density, then again a bit of high probability density, then at the center it is like very high probability density. This one in fact is the probability density. This red one is for this, very high at the center, and then when you go away it is low. So what does it mean? Does it mean that the electron will be at the nucleus according to Schrodinger? No, it is not. It is giving you the probability density, not probability. So what is probability? Now how to get probability is the talk over here. That's the discussion what we are going to do. Let us understand the difference between probability and probability density so that we can understand what is going on a bit better. Say I have got a football field and due to various equations on time and all, we have figured out that the probability density of football being in the D, because the goalie keeps it for a while before throwing it and the players keep it with themselves for a lesser time than the goalie keeps it, and we have figured out that the probability density is high over here. Now probability density doesn't mean that probability is high over there. I'm depicting probability density by dots and outside spaced out dots. That's a lower probability density outside. If I ask you what is the probability of finding the football, where is the probability of finding the football? Inside the D or outside the D? Most probably the football is outside the D. Most probably the football is somewhere in the field over here rather than inside the D, even though the probability density over there was more. Just because the area outside is more. Big area into small probability over there, probability density over there, and here small area into maybe thrice the probability density. This may not be more than that, this may be less than A, just because that A is much more than 3 times the area, it is 10 times 20 times more than that. So the point is, even if you have higher probability density at a point, at a region, the region is small, then the probability of finding the stuff over there would be less. Had we been discussing two regions of same area and one was having more probability density than the other, then where is the probability of finding more? The probability of finding the thing will be more in here where the probability density is high. So I hope you have understood the difference between probability of finding and probability density. So now this was area probability density, what I was talking about, and here the wave function square, the size square gives you volume probability density. It gives you volume probability density. So you have to multiply the probability density with volume to get the probability. Now if it was like a constant, I gave the probability over here to be p and 3p. If it is not a constant, then you'll do some calculus, some integration, and many of you would have not done integration by now. It is going to come in in a few weeks you'll be doing that course and you'll be okay with this part, but right now just try to understand what it means, what is the effect of, what is the outcome we are trying to achieve by doing that integration. Yeah, so now coming back to this model, here the probability density near the nucleus or at the nucleus is very high, so they have drawn a lot of dots over there, and as you go away these are spaced out dots, it is less. But if I ask you about this green volume, and I ask you about this green volume, this one, this green volume and that green volume, it is a 3D thing. I'm talking about volume, so you'll have to imagine this thing like an onion or something, and that onion skin's volume, the total volume would be how much? So that would be the area of the onion skin into the thickness. So we are going out in same steps. So unfortunately they have drawn it like larger steps over here. It is the same step. This thickness is same. This thickness, that thickness is the same. So that thickness is your dr. So what is the volume? What is the volume of this, say this green one? The volume of the green one will be whatever is the radius over there, 4 pi r square is the surface area into the thickness will give you the volume. So this you'll be doing a lot, volume of an elementary part, so don't worry about this thing much. about how I got the volume. You'll be getting it in no time when you have done this. So this is the volume. What I am trying to emphasize over here is, if you are at a more a shell or at a sphere which is much near to the nucleus, then the volume will be less, and when you are away, then the volume would be more. So even with low probability and high volume, they have made a volume graph over here. They have made a surface area graph, and the thickness dr is same for all of them. So that will make it a volume graph if you want to get it like that, understand it like that. You're seeing that near the nucleus, your volume is very less. The height of the graph is the volume is very less, but your probability density is high, and later on your probability density is less, but the volume is quite high. So where is it giving you the peak? Where is it maxing? So they have drawn this dotted line, and there where it is becoming maximum. So they are multiplying the probability density with the volume to get the effect, and this probability density into that volume, if you integrate means doing volume for all of these peels, all this green purple green purple. If you do the integration, what should it give? You tell me, what should it give? That's the probability density, and that's the volume, and we have done it all over. So total probability is always 1. That's 100%. If I say that this is the region, that football field has to be in the football field somewhere, either in the D or outside the D. So the probability of being inside plus probability of being outside has to be 100%, which is 1. So among these, it has to be somewhere, and this keeps on going till infinity. That's another story. So that has to be 1. So that probability, and to get that, if the function is not directly giving it as 1, they normalize the function, which is again not in course. You don't have to know that. So all that you will be doing when you go for your engineering, and suppose you have taken up chemistry. So coming back to this graph, that's another fact, that area under curve is given by integration of y dot dx, if y is a function which is plotted on the y-axis, and x, your dx is the increment along the x-axis. So if you have any function, if I want to get the area under the curve y, so I'll do an integration of y dot dx, and will give you the area under the curve. So here again, you are seeing that this is almost in the form of y dot dx, because x is nothing but r, your x-axis is nothing but r. So that's your, instead of dx you have a dr. So this, if you plot along the y-axis, if you plot this along the y-axis, which they have done, if you plot that along the y-axis, then the area under the curve will be what? That will be the total probability. So if you want to know what is the probability that the electron is from this point, like 0 radius till this radius, you get that area, and if it comes as say 0.4, then 40% chance the electron is there, and that area with all going till infinity must be 60%. So if you want to get it in any one area, so come over here. So they have shown it over here. If you want to know what is the probability of the electron being here, then this thickness of the green bar was your dr, that's the thickness of the green bar, and the height of the green bar is your psi square 4 pi r square. Psi square 4 pi r square, they have omitted 4 pi over here because it is just a constant and the graph will just get stretched. They have put that 4 pi over there, and we generally find it fit with the 4 pi, so that the total area depicts you the net probability, and there's no modification to that. So I hope you have got an idea that we have got 3. I'll just again put a gist to all this. We have got 3 kinds of graph. One is of the wave function psi. That is the outcome of the Schrodinger's equation, and it doesn't depict the probability at all. It doesn't depict the probability. It gives you information about the wave nature and all other informations like energy and other stuff you can get out of it, but it doesn't give you the location. Now what gives the location is your psi square. It gives you the probability density. Now probability density, we have just seen that it is not necessarily the region of high probability. If the probability density is high within a volume which is also high, then only the probability is going to be high. So if you want to get the probability, you have to multiply with the volume in which you are talking about. So you have to get hold of, if I want to find the probability of, come over here, look here in that green region, then I have to get that volume. I have to multiply with that volume, and then I'll get a number which is less than 1. I'll get a number like say 0.2, 0.3, 0.02, 0.05 to know what is the probability of the electron being there. So the probability is got by multiplying the volume with that. Now volume, the elementary volume multiplied with the probability density is giving you the probability. In a graph, it can be shown as your psi square 4 pi r square being on one axis and r on the other axis, such that the probability itself becomes the area under the curve. And once you look at a curve, you are what visually you can figure out is the area, where is high area, where is low area. That area is directly going to tell you the probability. So in a curve, you are going to go ahead in steps of a constant, a very small infinitesimal amount. That is your calculus term, and I have introduced that term to you. Infinitesimal amount you go forward, but the same amount forward all the time. Then this area is effectively the height. You look at the height of the curve, because you're going to multiply with the same breadth all the time. So the height of the curve is going to tell you the most probable region. So what is the most probable region of finding the electron for say a 2s? This height is highest. Is this? No, it is not, because this was psi curve and has nothing to do with that. This height is the highest. Is it? No, it is not. It is probability density is high over here, but not the probability. So we'll come to the probability diagram. Here, where is the height highest? This height is the highest. So that means that most probably the electron would be over here. It can be at other places also, but there is no chance. According to Schrodinger's equation, there is no chance that it is at this point, at the node. I hope you have understood this. Try to basically understand that we have three graphs, psi square, and 4 pi r square psi square versus r. All of them versus r. All of them versus r. This is your wave function, this is your probability density, and this guy is the probability graph. So this graph is going to tell me the shape and not the other two. Let's go on to the next slide. So now you can see that they have drawn this probability density and the radial probability distribution. They'll call it as RPD, radial probability distribution, which is 4 pi r square into psi square. So they have plotted both of them. Now you see that at the nucleus, the probability density is very high, but the volume of the nucleus itself is so low that when you multiply with the volume, which will be 4 pi r square into dr being over here, and 4 pi r square of the nucleus means radius of the nucleus, which is very low. So that is almost equal to 0. So it will be 0 at 0 radius at the center of the nucleus. There is no chance. So this graph goes down. This is not a very expanded one. This is not a stretched out one, but you see the graph is going down. The graph is like this. it goes down. So this guy goes down when you multiply with r, high value but r 0, multiply with r which is 0 at 0, when r is 0, when you multiply with 4 pi r square, this graph is going to turn back and come to 0. You just turn back and go down, so it goes to 0 over there. So that's your probability graph. So what they have drawn over here, what is this, is the probability density. In the dotted diagram it would be like this, very high probability density, but it is not giving you the shape. This probability density is not giving you, it will give you the region will be of what shape, but it is not giving you the actual location of the orbital. This guy is giving, this guy is giving, and I hope we have a better one. We have a bigger one over here. I'll just explain with this one. So you see very high probability density at the nucleus, so very dark over here, very dark over here, then zero probability density, so it becomes white over there, nothing over there, and again the probability density is higher. Now if I take this whole volume and take the whole blueness all together, then this total blue thing is more than that in between thing. In between is very dense, but it is not that much of volume. So the probability of finding over here is more, and then probability right at the center, which cannot be shown, which is not very well shown in this, is again 0. So they have drawn the probability density graph, they have not drawn the probability graph. So they have not drawn the shell. So this is not the shell, this is the probability density. So high probability density over here, and high probability over there. This is ultimately the probability graph. This height, this is the most probable radius where you can find it, and there is another radius over here. So what is it telling you? What is it telling you? What is this graph telling you? This graph is telling you a very funny story. It is saying that S is not one spheres, but it is two spheres with higher probability of finding on the outer sphere, because this probability is higher than finding in the inner sphere. And your 3s, that's your 3s, 3n3l0 means 3s is 3 spheres. Here the red one is where you can find, then here, and then here, among which this one is having the highest height, hence the highest probability. So a 3s electron can be in these 3 spheres, and the inner one looks like closer inner to this 2s shell itself. So I'll draw a 2s shell in, say, green. That's your 2s shell. So 2s itself has got 2 shells. So that is your green shell, green shell. Your green is your 2s. Green is 2s. Then say red is your 1s. 1s is somewhere here. So it is showing that a 2s can be within 1s. That is, your pink is your 1s. And your blue is your 3s, and 3s are in fact 3 shells. So the innermost of it is maybe within the inner of the 2s itself, and then within the outer of the 2s is your 3s next shell, and then the next shell. 3s has got 3 shells. So the inner shell of the 3s maybe I mean it is in fact, see the radius, it is just more than 2, just add 2, and this guy is more than 2 for sure, right, according to their diagram. So it is more than 2 for sure. So this guy, this radius is say 3, then the S shell outer radius is okay, it is quite outside, it is around 7, but the inner hump is at 2, so it is within that shell. So what we are seeing over here is that 2s 3s need not be one shell, and there is no end to the shell. Another thing is there is no end to the shell, the density becomes very low. So we generally make a surface diagram and we close it off, like 90% of the thing will be within this region and let the 5% or 10% be outside, that doesn't matter. So we make a boundary diagram. I'll show you that. Yeah, this one is also a cool one. So they have drawn for 2s. Yeah, this is the actual one. This is the probability density, but this one is the probability one. You see at the center it is white. At the center it is white means it is zero probability. That is the thing. At the center it is white. Then what you see is this small hump. That small hump. That small hump is the next one inside, and the big hump is the outer one. The big hump is the outer one. Between the small hump and the big hump there is another white region where there is no probability, so I hope you are getting it. I can show you a bigger and a better diagram. Now this is again your this figure. It is showing at the center also, so it is, this figure is for your probability density because it has shown at the center. So it is not a very nice one. But this one, if you look at this diagram again, it is showing at the nucleus also. If it is showing at the nucleus also, it is probability density. So at the nucleus it should be 0. If you are showing probability at the nucleus, it has to be 0, which they have not put. This, you see this part is 0. Here the probability at r is equal to 0 is 0. Here they have not put as 0. So rest everything is right. Rest what happens for 1s, that's a purple graph. For 2s it's a green graph. You see a region where there is no probability of happening of the thing having, that has been depicted as node. Then again this is the green, this green graph, this is the green region where again you have, for the 3s you see there are two nodes here as well as here, two nodes, this point as a node and that point as a node. So you have two nodes here as well as there. Mind you, we are just going outside along the radius. We are just going like that along the radius. So when we encounter, so let me just go along the radius outside. When we encounter a white region, meaning to say that's a node. When we encounter high region, that's a high point. Let me draw this. In the here it is, center is also high point, so it is a probability density curve. Then comes a node, this one, this white one, that comes as a node, and again comes a high point and then goes down. So high, three high points are there and two nodes in between. Nucleus is never called a node. That's your psi square graph. That is the density over there. Now you multiply with the radius. This outside radius is more, so this hump is going to become the higher one. This becomes, after getting multiplied with a r square, you see that r square is getting multiplied. This small hump becomes a big hump, and this very high hump, r is 0, goes down, crashes down to 0. It becomes 0 in the point, and this one is going to tell you the actual location of the orbital. Yeah, so the big revelation right now is that 3s is these three orbitals, with the most likely place of the electron being in the outer one rather than the inner one. Okay, can you tell me what is wrong in this graph? Can you look at the graph and tell me what is wrong in this graph? Just pause the video and do it, and then you resume. What can this graph be for? It is written as phi over there, psi over there, n is 1, n is 2, n is 3. So if it is for n is equal to 1, it has to be for s. So it is for, this graph is for 1s, because n doesn't have a p, n doesn't have a d. This graph, the other graph, would be for 2s, and the third graph, which is named as 3, must be for 3s. So what is wrong in this graph? Since the graph is going to the negative side, it is a wave function graph. It is not the square of the wave function graph. It is not the square of the wave function graph. Right? 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 So it is not square of the wave function, it is the wave function graph, because it is going on the negative side. Now, if it is the wave function graph and it is of s, then will it be 0? n1 has to be 1s only. Is wave function of 1s touching 0 ever? No, it goes like this. 1s goes like this. 1s goes like this. So maybe they wanted to do the probability graph, but then that will not be negative. So this is nowhere it is right. Your 1s itself is wrong. So this graph is wrong. Your wave functions for s, all of them, like 2 frames back it was shown to you, all of them start from the top. The p wave function starts like this. This is a typical way for a wave function of p. P starts with a 0. The probability of electron, the probability density, even the probability density of the electron being at the nucleus is 0. For s, there is a high probability density. It doesn't reside at the nucleus. Mind you, I'll give you another reason why it doesn't reside at the nucleus. There are several reasons. So in terms of velocity, that's, I mean, in energy it will sound more authentic, but in velocity it will sound more simple to understand. Your Heisenberg principle, delta x into delta p, has to be greater than h by 4 pi, right? It has to be greater than equal to that. So if the electron is located in the nucleus, that means we have located to a very precise amount, because nucleus is a very small, very tiny diameter thing. So that is what we are going to breach this uncertainty badly. We have located to a very pinpoint kind of thing. So let us just put that pinpoint value and put the nucleus size as, say, 10 power minus 15. Suppose the nucleus is 10 power minus 15 meters size. Okay, so that's around the size of a nucleus of hydrogen we are talking about, by the way, and multiply with mass. Mass is your 9.1 into 10 power minus 31. So forget about the other numbers. 10 power minus 31 into delta V. Even if we are going for equal to, that means we are wanting, we are going as precise as possible. We'll have a equal to h by 4 pi. So what does my V comes at? Your h is 10 power minus 34, right? So do away with the 4 pi and all. It's not going to make much of a difference. So what your delta V comes as? Delta V, what does the delta V come as? The 10 power minus 31 will go on the other side, will become 10 power minus, with this 10 power minus 3, and this 10 power minus 15 will go on the other side, and it will be 10 power 12. Now the error in measuring the velocity of the electron, if it is there, will be 10 power 12 meter per second. Speed of light itself is 3 into 10 power 8 meter per second. the speed of a particle more than the speed of light, that's a impossible situation, so that can't happen. So that speed, it can't speed up to that amount. Nothing can breach the speed of light. So it is, and Heisenberg principle stands tall. You can't say that this goes wrong. This is all right. This is absolutely all right. So the thing is, what is wrong over here is your delta x, your location of the electron. Location of the electron cannot be pinpointed to the nucleus at all. Same thing you can do with how much of energy will be confined, or how much of energy the electron should have to have this kind of thing. So it will be beyond all possibilities. Okay, we'll see the next frame now. So we have done s orbital. We'll look into the p orbitals now. So we'll straight away check the probability. Instead of going for phi, psi or psi square, both of it is not going to give you the actual location. Let us straight away go for the probability. Mind you, psi square of p and 4 pi r square psi square, the probability or the probability density will look almost the same. So s was a problem. S starts from up, the sigma. P starts from the 0 itself, so it is not a big problem. It starts from there itself, whether you are doing this or this or this. So looking at it, what do we see for 2p? What do we see? That's the nucleus. Okay, I'll make the nucleus here. As I'm going higher distance, as I'm going farther, the probability of finding the thing is increasing. So I'm making that lot of dots. That is what they have made over here. And then as you go even farther, the dots reduces. So here, this region was a big probability of finding. Before that low, after that low. So the shape, to get the exact shape, how do you know it is not a full sphere? When you go around, it is not a full sphere. You're just going outside radially. What about that? So you have to take an angle theta and go around. So theta diagrams we are not making. So when we go along phi, either theta or phi, we go along the theta or go along the phi, what happens is this again drops down. It again drops down. So here the diagram is made when you are going along the radius. Radius is like this. When you are going along this, low probability over here and then high probability over there, and then again low probability. So you're going along the radius like that. You're not going outside with an angle of theta. You're not going outside. If you go outside, then again you will see that the probability will drop down and you'll come to a region where there is no probability. So they have depicted the probability density over here. So this is the probability density. So as you go along the radius, first there was no probability density. It increases. Then again it starts decreasing. If you go outside, which we have not drawn, people will draw to get the whole shape. So if you go outside at an angle, because wave function for an angle we are not doing right now, we are not doing that, it's not for the syllabus. So we'll go outside and we see again it drops. There comes a point where there is no probability at all when you are going along the angle. So when you go along the angle and find a region of no probability, that is called an angular node, because you go along the angle and find a region of no probability. So you can very well see that it would be a plane. You can see in the diagram it would be a plane like that, where there is no probability. Either this side something is there or that side. So that's the plane. Here that's the plane. There is no probability. So these are called angular nodes or nodal planes. They are nodal planes. Angular nodes are also called nodal planes. So Can you tell me, while you were going along the radius, look at this diagram, did you find a node? No probability. No, you did not. Nucleus and infinity are not called nodes. The probability drops down. At infinity it is not 0, it is almost 0. At nucleus it is 0, but nucleus is not called a node. After the nucleus, the nodes, you will start counting the node. So as you go along the radius, as we went along the radius over here, what happened? The probability increases and then decrease. We did not find any node. So this guy, this 2p thing is having no radial node. 2p has 0 radial node. But the 2p, one of the 2p's we are talking, say 2pz, when you go along the theta, along the angle, and before it comes back, it has got one node over here. It has got a plane. If you go 360 degrees, then you'll encounter the plane again, by the way. So you'll get one nodal plane. It has got one nodal plane. So how many angular nodes? That 2p is having one angular node. 0 radial node, one angular node. So I'll be discussing that in the next frame. So I hope you are getting that. If I draw a 3p, now again, like your 2s was a surprise, it was a double shell. 3p is a double dumbbell, not like your D kind of double dumbbell, one after the other. It is in the same axis. So suppose this is your 3px. So apart from being inside, and this inside guy, this tiny inside guy may be within, or it is within the 2p. It is under the 2p. I'll draw the 2p with green. So your 2p would have been here. That green was your 2p. Again, what we are seeing is what we saw with the 2s and the 3s, that 3p is inside 2p and outside 2p. I mean, way outside 2p and slightly inside 3p. So that's your 3p. 3p is here as well as there. So these are the two regions. This one is this inner one, and this one is the outer one. Okay, and your 2p, you can see that 2p radius was more than the inner hump. That's your 3p inner hump, and that's your 2p outer hump, or one hump only. It was having one hump only. So it has got two humps. While you are going along the radius, you encounter that some 3p electrons will be there, and then you again encounter, and more you encounter outside rather than inside. But when you go angularly, this is like you are going in 1D. When you go angularly in the plane, then what happens? These humps go down, and you have your nodes coming again. So angularly, when you go, what would you imagine? Again, this line, what I have drawn, it will have a depth and it will become a plane. This will be the nodal plane for both the inside and outside humps or not. Whether from inside or outside you went with an angle, you'll see nothing over here. That is when you're going with the angle, and that is called an angular node. So it has got how many angle node? Again, one angular node only. So 2p was also having one angular node, 3p is also having one angular node. What can you deduce from that? P means L is equal to 1. So whether it was a 2p or a 3p or a 4p, what would you imagine a 4p will be? It will be 3 humps, right? 3 humps. It will be something like that you can find it in 3 dumbbell places, and most likely the outermost dumbbell place will be the most likely place. But how many angular nodes will it have? Again, this region will be angular node or not? So here they have drawn the density diagram, and you can see for 3p, that's the angular node or nodal plane. That's the nodal plane where you find nothing, because you have gone along the angle theta, and you go along the angle theta, and that's the region where you get nothing. And these places, how many radial nodes you have got? So if you go along the radius, so I'll just make it, I've just messed it up over here, so I'll make it like this. Along the radius I go up, along the radius I go up. So discounting the nucleus, where do I find no probability of getting it? I have a white region over here where there is no probability. So that white region is this. So when you go along the radius, then this region you are having no probability, that's your radial node. Can you figure out a formula for radial node itself? Your 2p was having 0 radial node, 2p 0 radial node, and 3p is having 1 radial node. So what can be the formula? 4p will have how many radial nodes? 4p, let me make a 4p. So when you are going outside along the radius, how many times you see that there is no region? There is one over here, nothing between the two dumbbells, nothing over here. You have discounted the nucleus, and again you will find nothing over here. So your 4p is going to have 2 radial nodes. So can you connect this n and l? N is the shell number and L is the type of shell. So your L is 1, N is going up by 1, and radial node is also going up by 1. So N is directly linked to the number of radial nodes. So can you say for P it is N minus 1 minus 1? 4 minus 2 is 2, 3 minus 2 is 1, and 2 minus 2 is 0. So many radial nodes. Get the point? So in fact you are going to see that the radial node will be n minus L minus 1. L for P happens to be 1, hence n minus 1 minus 1. So this will be the formula for radial node for any shell. So if I come back to this, in fact let me go forward and show you this one. I've drawn 3s as well as 3p over here. So when you are going along the radius, how many times you are encountering a radial node? That means no probability region. Between the red and the blue there would be one over here, and between the blue and the red again over there. So we are getting 2. In this we have got 2 radial nodes. For 2s we have got 1 radial node, that is over there, and for 1s, sorry, for 2s we have got 1 radial node, and for 1s there is 0 radial node. So the formula what we proposed of radial nodes, radial node n minus L minus 1, will it work? Let me check out. Say for 3s, 3 minus, what is L? L is S, S means L0 minus 0 minus 1. So what is it? What does it give you? 3 minus 0 minus 1, it gives you 2. Yes, we had 2, that's your 2. Similarly for 2s, it will be 2 minus 0 minus 1 will give you 1. So this formula is working all right. Now 2s has a radial node but 2p doesn't have. So what you can say is, if it is the first of its kind in a shell, if the orbital is the first appearance like S has got a first appearance in 1, P has got a first appearance in 2, D has got a first appearance in 3, F has got a first appearance in 4. All of them, whenever it is a first appearance, there will be 0 radial nodes, 0 radial nodes. And the second appearance will have 1 radial node, the third appearance will have 2 radial nodes. First appearance 0 radial node, second appearance 1 radial node, third appearance 2 radial node, first appearance 0 radial node, second appearance 1 radial node. As you go up, this is the radial node we are talking about. Here is where you don't find anything. Okay. So the radial node is at that radius you can make a whole round, you can make a whole sphere around it. So it is spherical shape. Radial node is spherical shape. Radial nodes are spheres. Got it? So you will have in this dumbbell, you'll have a depression of a spherical kind. The red piece, you can see it is having a depression of a spherical kind in it. Now comes D. So D, as I have shown you, it is a double dumbbell. It's a double dumbbell. So D has its first appearance. D has its first appearance in 3. So by going by the logic of first appearance, let me just draw something for you. This is your 1s, this is your 2p, this is your 3d. Obviously the heights and all will not be same, the shape is same, the radius, the distance from where I'm talking is not same, but I'm just showing the shape of the graph. It is not having a double hump or a triple hump. The first appearance of a shell of a orbital, first appearance, like S is happening for the first time in first shell, P is happening for the first time in the second shell, D is happening for the first time in the third shell. So all of them will have the same number of humps. That is a single hump. That's your 3D. So if you can relate, that's your 3D, that's your 2P, and that's your 1S. 2P was having a single hump, 3D is having a single hump, 1 is having a single hump. What will have 2 humps? What will have 2 humps? 2 humps. 2 humps touching a 0. 2 humps. So this is the second appearance of S, which will be a 2S. Second appearance of P, which will be a 3P. Second appearance of D, which will be a 4D. So 4D graph will look like that. So I hope you can remember when they ask you for a graph and ask you that which graph can it be? Which graph can it be? They're asking the radial probability distribution. That means a 4 pi r square psi square with r. If you see 2 humps, you think of the second appearance of whatever S, P or D. If you see 3 humps, it is the third appearance of S, P or D. So can you tell me how will 4F look like? 4F is the first appearance, it's a single hump. Okay. Now again 3D radially. If I go radially, so I'm going radially, maybe I'll show for, which one shall I show? I'll show, none of them are placed in a very good way, so I'll show for this. I'm going radially out like that, in between your X and Y axis. I'm going radially out like that. Sorry, in between your Z and X axis. So when I go radially out, I get a big balloon and then nothing. I'm not going angularly. I'm not going angularly. If I go angularly again, I'll get a low probability, then high probability, then again low probability. So you're getting two nodal planes when you're going angularly. But radially, you're not getting any nodal plane. Radially, it is, when you're going out, it is just becoming high, 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 high. That means if I try to draw, then this will be the thing. The electrons are very high, 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 and then again low. So that is what happens if I draw on the other side also. So it is creating a dumbbell. I don't know if I go in a 3D, if I go that way, theta, then maybe it was creating another dumbbell. I don't know, because variation is theta is not known, but they have drawn, and we know it not because of this graph but because of other graphs, that again you'll go to zero probability and a high, 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 high over here, and then again a zero probability. So you'll get a dumbbell in this axis. So when you go from here to there, this 90 degrees, you go from here to there, in between this region, you have no probability. So you got angularly I've gone, so you get an angular node over there. And similarly over here, you have no probability. When you go from here angularly, you get an angular node. So how many angular nodes on nodal plane we have? We have two nodal plane for any d orbital. For each d orbital, we have two nodal planes. So all 5 d orbitals, we have 10 nodal planes. And the nodal plane for the dz square looks very cool. It's a cone shape. Will not defy that it will not have. Sometimes some books say that it will not have a nodal plane. Yes, in this nodal plane, in this plane, this is not a nodal plane, because this guy, this ring is appearing in that plane, so it's not a node. But when you take a cone, like this, and that cone is having there's no chance that the electron will be there in the cone. That was your ring, that was your dumbbell, and in this different color I'll draw a in between thing. That in between thing is having no probabilities, that comes as a cone around it. Okay, so that's a nodal plane for the dz square. So we saw that the p guy was having one nodal plane. We are seeing that d, which is a double flower, double dumbbell, is having two nodal planes, 1 and 2. Right hand corner I am drawing it. So we are seeing that this is having a two nodal plane. This p was having one nodal plane. F, we have discussed that f is 3 flowers. Three dumbbells. How many nodal plane do I guess there would be? When I go from here to there, this is a nodal plane. When I go from there to there, that will be a nodal plane. And when I go from here to there angularly, that will be a nodal plane. So I'll get 3 nodal planes when I'm going angularly. So for P I had 1, for D I have 2, for F I have 3. So it is not at all depending on your N. Why it is not depending on N? I'll just make some space over here and draw. That's your 2P, and that's your 3P. Now whether it is a 2P or a 3P, the nodal plane is this, right? When you angularly go, you get only one region, there is zero probability, right? Similarly, for D's, that is your 3D, the first appearance of D. That's your 4D. That's your 3D. That's your 4D. That's your 2P. That's your 3P. The 3P is over 2P. You have 2px, suppose this was 2px, then this is 3px over the 2p. And I mean this inner thing is not the 2p. 2p is somewhere here in between over here, but the 3p itself is having two dumbbells in the same way. But nobody stops from this being the nodal plane. So here also this was the nodal plane. Now your 4D is like this, wherein mind you the inner one is not 3D. In 3D is somewhere here. 3D is somewhere. I'll draw with a different pen, say a blue pen. 3D is here. We agree 3D is here. But the 8 flowers I drew was all for 4D. So 3D is there. Now 3D had those green nodal planes. 4D will also have those green nodal planes. So what I'm trying to say is it doesn't matter whether it is a P of a 2 or a 3. It doesn't matter it was a D of a 3 or a 4. The number of nodal planes are same. Whatever is the nodal plane for 2P is the nodal plane of 3P. Whatever is the nodal plane of 3D is the nodal plane of 4D. So it depends only on the subshell type. So it depends only on L. So let us just write down the L value. What is the L value? L is equal to, for P we say L is equal to 1. For D we say L is equal to 2. For F we say L is equal to 3. So what are we seeing? That the number of nodal planes is the angular nodes is equal to the angular momentum quantum number, which is L. So angular nodes is equal to L. So what we have is a simpler formula, a very simple formula, that angular nodes is equal to L. And we already had that radial nodes was equal to n minus L minus 1. These were spherical shape and these are planes, so they are also called nodal planes except for the two conical ones. Sorry, except for the conical one in your dz square. So in F also the z cube will have conical nodal plane. I'll show you if it is there in the diagrams. So angular node is equal to L, radial node is equal to n minus L minus 1. Hence, if they ask total nodes, these are surfaces. Nodes are not points, they are surfaces, whether radial or angular. They are not points, they are surfaces. Surface. This one was coming like plane surface or conical surface. This comes like a round, like a spherical surface. So, and I hope to show you that shape in the diagrams above. So total node comes equal to n minus L minus 1 for radial plus L for angular. So what we end up with is n minus 1. That's your total number of nodes. And mind you, these are surfaces. Okay. So again you can see a diagram for the D angular nodes we have already shown to you. So the D angular nodes are two planes for each of them. For each of them there are two planes. So another diagram for you. That's it. Oh, I think I skipped it. I should have done this much earlier so that you would have got a better idea. But anyways, maybe I'll insert it. So what are angular nodes? Angular nodes can be found simply by finding out L. So that is what we have discussed right now. This your L, this is your P. L is equal to 1. right? That's again your P. Your L is equal to 1. So whether it was a 3p or it was a 2p, that's your 2p, that's your 3p, you'll have your angular or planar node or angular node or nodal plane same. That's your angular node. That's your angular node, right? Now what is your radial node? The radial node which was n minus 1, l minus l, n minus l minus 1, radial node. What will that be? Radial node is when you go along the radius, how many times you encounter zero probability when you are going along the radius. So here in this diagram it can be seen when we are going along the radius outside, this is where we encounter zero probability. This is where we are encountering zero probability, and it's a spherical region, right? So it's a spherical region. So your angular nodes are generally plane except for the conical ones, and your radial nodes are spherical. They are surfaces which are spherical node it is called. See, they have written it as a spherical node, and this one is your planar node. That's your angular. So that's it, guys. Now what I'll do is I'll give you some wave function equations to solve, and uh, in the tougher exams they'll just throw up one of those equations which was shown earlier, and they'll ask you to find the most probable radius and the nodes, where the nodes are. I just forgot to mention one more thing. Now just to sum it up, 1s was a single hump, 2p will be a single hump, 3d will be a single hump. 1s, 2p, 3d, all single humps. So 2s is a double hump, this is your 3p, it will be again a double hump, that's your 3p, that's your 2s. The 2s is having double shell, the 3p is having double dumbbell along the same line, double dumbbell. It's not like a single dumbbell which 2p was. And then you have your 3s, which is three shells is your 3s, that's your triple hump. So that's your 3s, a triple hump. So 4p, which is not there in this, 4p will be a triple hump, we have a 3d will be same as a single hump, right? That's your 3d will have single hump as 2s, as 1s had and 2p had. 2p, 1s, 2p and 3d same kind. 2s, 3p of the same kind, and 3s with 4p of the same kind. So 4p is not over here. So have a good look at the diagram, and you can compare the radius also. So let me just delete all this what I've drawn on top of it, and then take any one graph to compare the radius. Now what am I seeing? The big thing over here, what I'm seeing is your 2s is having a greater radius than 2p. 2s is outside and 2p is inside. So that's, mind you, 2s itself was having two shells in it, but outer shell is the main shell. That's the main area where the electron can be, I mean area under the curve. So that's the volume where the electron can be. So that's the outer shell, and your p is within it. The most probable region of P is within it. Your P is here, the other P is here. It is having a greater angular momentum than that, but the energy, this energy and that energy will be same. So I hope you got that. Your 2s is having same energy as 2p. The 2p is inside. Now what you can see, let me just compare the 3s, 3p and 3d. 3s most probable radius is, so maybe I'll just go on to the 3s one. So the 3s most probable radius is this, like it is showing around 13, which is in fact 13 by the way. Most probable radius, it comes around 13. Okay, I'll tell you a surprising thing here also, but let me just complete. Your 3p is inside that. That's your 3p location. That's your 3p is inside, and your 3d is even more inside. That's your 3d location. So that's your 3s, big one, in which is your 3p, and inside which is your 3d. So your 3d lies within 3s, within 3p, which is within 3s, but 3s itself is not like one shell, it is 3 shells. So 3p itself is having 2 shells. So the inner of the 3p, the inner of the 3p, I guess here, it is drawn very lightly. Inner of the 3p and inner of the 3s, I wanted you to compare, but you can have a better graph and compare that. So the inner of the 3p is inside. So inner of the 3s is somewhere over here. That's the inner of the 3s, and you have a still minute inner there, not the nucleus, mind you. So you have 3 shells of 3s. So that is how it looks like. So I hope you are getting a better idea. And this one I had taken for a, so you can pause the video and compare it. You can pause and compare it. 1s radius happens to be at the A naught, where your A naught was 52.9 picometers. 1s happens to be that, but if I recall the Bohr radius, the next would be 4a naught and the next would be 9a naught. So that was your Bohr's n equal to 2 and n equal to 3 Bohr's. But over here, if I compare the s, if I feel like s is what should represent the Bohr's orbits, the s shell, then it is not, by the way. Your shells n is equal to 2 is having a radius of, let me just go to n is equal to 2s. 2s most probable is over here, right? That's the most probable, that's the most probable. So it is around 5. It is not 4, it is 5, and it is the accurate graph. This is the accurate graph. So this is at 5, because I know the values from some other data. So I was just hoping that the graph is accurate. And your 3s, that's your 5a is your 2s. The 3s is not at 9 but at 13. Let me see where they have drawn the 3s. 3s is this blue one, and blue one, if I go down, it is somewhere near to 13 what they have drawn. So 3s is here 13. So it is not where the Bohr's radius are, but then we can say that this is the most probable one but Bohr never said about the p shells and the d shells which are inside. So inside the 13 is your p's, is your d's. So effectively you can say it will go down from 13 and will be around this one also. The outer is your s, your p will happen to be inside. 2s is the outer covering, it is the outermost, most probable. Then you have a inner of the 2s itself and you have a p also inside. So effectively it will become less than 5 and maybe it becomes 4 and it is okayish, but this is the actual one. So when you do the when you study the spectrum, the line spectrum and the fine line structures and all, then this is, when you zoom in, zoom in, zoom in, and when you are seeing, then this is giving you the right picture, this is giving you the right jumps, and the Bohr was giving you almost the right jump and not the exact one. So you can pause the screen and have a comparison over here. All of them I have just put it on a single line if you want to compare. If you want to compare, there are with different colors, so it is a easier comparison than earlier. So if you want to compare the inner humps of 3s with the outer hump of say 2s, that kind of comparison you can do over here. That is never asked, that is never asked, it is just for your own curiosity you can look into. And this is a cool one which I found out. So this is a cool diagram on the net. So let me just illustrate one or two over here. These are your S's, by the way. That's your S, that's your S, that's your S. The spherical ones are your S. So which S it is? It is 2S. So you are seeing two spheres and a node in between. This is your 3S. So you're seeing three spheres. 1, 2, 3. They have shown a density diagram, so they have put on the nucleus itself. So just think that at the nucleus it is dark over there. Just think that all rest will be okay, because the density diagram in the rest, apart from S, the density diagram and your 4 pi r square, this diagram matches. Apart from S, it matches in P and D. So in S you have to put a dark spot in the center yourself, because to get the probability and not the density. Okay, so just to show you, I'm just putting a dark spot over here in between. That nucleus you can't have. Okay, so let us look into the F, because we have seen the others. This is the first of the D kind, is it not? Is it not? What is it? 3, 2, 1. The quantum numbers are 3, 2, 1. What does it mean? It is 3D, and 1 means it is one of the orientations, and it is not 0, so it is not a z square. This is a 0, so that's a z square. You see, this one is shining. This is a 3D z. You can call this as 3D xy. This is a 3D z. So that ring is shining like this, and that's the nodal plane you will have. That's the nodal plane you are going to have. Now your 4s, see 4 regions. The outer one, outer radius is coming more than the Bohr radius. Outer radius is coming much more than the Bohr radius. Now what is this? This is D, but I don't want to look at the D, I'll just want to look at the F. So we'll go to 4, 3. This is your F. That's your F. So we'll look at a regular F. This is your F0, FZ. Because M is 0, you can check M is 0. So this is your 4FZ. 4FZ is having that 2 rings. Apart from the dumbbell, 1 ring and 1 more ring, right? There are 2 rings. Get the point? So it will have the conical nodes over there and a flat node over here, flat nodal plane over there. So it will have the 2 angular nodes. So you can see when you go angularly, Are you encountering this region of a node and that region of a node? Yes, you are encountering, right? So even if it is a Z you are encountering. Let me look at a F regular one. So this is your 4F, which has 3 dumbbells. So 3 dumbbells. So you have 3 nodal planes. So those are the nodal planes where it is all dark black black black. So this black region is the nodal plane. This one is another dimension, so you can't see. This is like you have to see from the top, and this is beautiful. This one, what is this? This is second kind of, this is 4D. First D appears in 3, so that will be like this one, but the second D will have inner as well as outer dumbbells. So I just wanted to look at the second P, means 3P, this one, inner as well as outer. And then a 4P, have they drawn a 4P? Yes, they have drawn a 4P. This is crazy. 4P. So in the same axis you have 3 dumbbells, like I was just showing over there. 1, 2, 3 in the same axis. So that's your 4P. 1, 2, 3. Does it change the fact that this nodal plane, which was for a single one, like this nodal plane was for 3P first kind, 3P first kind, says 3Px, and that's a 4Px, and let me get a 2Px somewhere, that's your 2Px, see 211, that's a 2Px, all have the same nodal plane. Can you see that this nodal plane, that nodal plane, and that nodal plane is same? So I hope you have understood what is nodal plane and what are spherical nodes. I'll just want to show you one more diagram. I'm not getting that. I'd put it somewhere, but I think I removed it. Now few extra stuff just for advanced exams for your IIT, JEE advanced, and sometimes in mains. Maybe in mains they will not ask you to calculate, so the calculation stuff will be for the advanced. For mains will be conceptually should be knowing. Even for NEET and AIMS, conceptually just try to understand what I'm going to tell over here. Now if I'm studying, say let me study 2s, let me study 2s. 2s has 2 humps. Let me study a single hump first. 2p is all stressed out. I don't want to study 1s because it is very peak and it is going to spoil my, had I got a separate graph of 1s I could have done that. Let me take a 2p and do it. I'm talking about that graph and I'm going to do some stuff. Now what is the most probable radius of this 2p? Again you see this 2s is coming at 5a naught. It's quite an accurate graph. So it's the same graph what we were doing earlier. Anyways, this is your most probable radius. Now if I ask you, this thing is called, let me write over here, most probable radius. Okay, say it was a 1s. Okay, it was all stressed up. Okay, since I'm talking about radius, it's a most probable radial distance in fact. Now if I ask you to find where is that, before that I hope everybody is clear how to find nodes. You'll have in the Schrodinger equation, you'll have some constant stuff over here. You'll have a linear or a quadratic or biquadratic or a cubic in R, depending on how many nodes are possible. So if you have a quadratic in R or whatever, and then e power some stuff over there. So if you have this, to get the get the place where the node is, either phi square is equal to 0 or phi equal to 0, psi equal to 0, because psi 0, psi square 0 will be at the same space, so same spot. So when psi is equal to 0, you can straight away put, you don't have to do a psi square. So, and to do a psi square, I already told you, you should know the complex conjugate, which is not required. So say straight away psi equal to 0, when you do, you'll get the nodes. Equal to 0 will give you the nodes. So nodes I have discussed in the first second frame of this lecture, so I'm not going to discuss nodes again. You just watch that part, because that time node was not told, but it was told that when the function will become 0. So how to find out that? Now the most probable radius, how to get this, if the function is given and all, the graph is not given, the function is given to you, and to get the most probable radius. Most probable radius happens when it is peaking and going back, right? So at the peak, we have a concept of maxima minima which you will be doing very soon. So if you have a y versus x graph which has a peak, what do you think is the slope over there? How to get this x1 location where the slope is flat? At the peak, the slope is becoming flat, the slope is becoming 0. So what you do is, you find the slope of the graph, which is dy by dx. It will come as a function of x. It will come as a function of x, a new function of x called f dash x. Now you'll put that f dash x equal to 0 and get the value of x. Get the point? You get the value of x, that is where it is going to peak. A very simple example would be, say y was 2x minus x square. Where is the peak of it? Okay, if I didn't know this differentiation and all, it's a quadratic graph. I can very well draw the quadratic graph. It is like this, where the 0 is at 0 and the other 0 is at 2, right? So you can factorize it. It becomes a 2 minus x into x. So when x is 0 as well as when x is 2, so where do you think the peak is? The peak is at x equal to 1. But this is a known graph. Suppose I am using this funda. So what I say is, I'll find the dy by dx. What does it give? It gives you 2 minus 2x. That's your dy by dx. You have differentiated it. Now that gives you a slope all over. At different x's there is a different slope. At which x is the slope 0? At what value of x? What is this x such that the slope is 0? So what I say is, I'll put this dy by dx equal to 0 to get that x. So I'll get a 2 minus 2x equal to 0. That means x equal to 1. So that's my answer, x equal to 1. So that is how you'll do it. You have the function. First you should know the psi square function to get the actual probability. It has to be the radial distribution function, not the wave function. Wave function differentiation is not going to help you, because wave function, like 1s, the distribution goes like this. It has no slope over there. It will not fit in, as I have explained earlier. So you'll differentiate that with respect to the axis, which is r axis, and after differentiating, put it equal to 0. If it is having multiple humps, then you'll get multiple places where the slope is 0. So you'll get more than one answer, as you'll get r1 as well as r2. Then you'll have to actually plug in that r1 and the r2 in the value which is getting differentiated and see which is highest. So much is not going to come. Very simple. If they are asking you to differentiate and find the highest point, very simple graph is going to come. Now even, simple function is going to come. Now the next difficult thing, this was number 1 difficult thing. So note it down what I've said. I'm just rubbing the screen so you can pause and note it down. Yeah, so the next stuff, this is your radius most probable. They'll ask you what is radius average. They'll not ask you to calculate. They'll not ask you, don't worry. They may give some logical question on getting the average radius. Let me make a more convenient graph for myself. So I made it. This is your radius most probable. That means at this radius, the probability of finding is the highest. But remember, what was the meaning of the area? Area was simply giving you how much is the probability. If I see both side areas, what I see across left side and right side of the most probable radius, the area is not same. The probability of finding on this region, in this region, is more than finding that region. So if I do an average, my average radius is going to come somewhere over here, R average. So when we'll do integration, we'll be doing some averages in your physics also, in current and all, we'll be finding these kind of stuff. Okay, so this average thing we'll be doing. So it is actually, you'll have to integrate it from here to there, get the whole area, divide by the whole span. So it goes on till infinity. So you'll have to apply a technique, so which we cannot discuss in this chemistry class. So forget about that. What basically what you have to know is your radius average in all these curves, you'll see, is more than the radius most probable. So your Bohr radius was 9a for third shell, 9a naught for third shell. Your 3s was 13 a naught, and your average 3s average will be even higher. It will be even higher, maybe 16 a naught. It will be even higher. Get the point? So the point is, what is your average radius? Your average radius is given by finding the total, finding the total area divided by the total span, which you don't have to do. What you have to remember is whether the average radius is left side or right side of most probable radius. So you'll check out the area of the given graph. So if they have not drawn an abnormal graph and it's a normal graph, then the right side will have more area to it. They're most probably not going to give you humps and all. If they give you humps, it will be an actual calculation what you'll have to do, which will become quite difficult. So right side for the first occurrence ones, first occurrence is 1s, 2p, 3d, 4f. All this have similar graph. Your most probable is here, your average is going to be there for all this, all this. Try to understand. Now, if you have digested everything, there are some questions which come only for advance, and I'll give you as an assignment. So after the video, it will be given as assignment also. So I'm just posting it on the video also, so you can look at the questions and try to give that answer. I'll read one or two. For a 3s orbital, your psi function is given for 3s. For 3s, it has got how many humps? 2 humps. So it is rightly coming as a quadratic over here. We have already seen the function earlier listed, so they have given the right function. What is the maximum radial distance of node from the nucleus? So they are asking you to find the nodes and the outer node. So how to find the node? I guess you know it. So these kind of questions, let me see if they have asked the most probable radius also or not. The normalized wave function. What do you mean by normalized wave function? It's simply the wave function, but then they are ensuring that when you do the probability, that probability comes as equal to 1. That is your normalized wave function. So don't worry about the words, just keep on reading. So the normalized wave function is given by la 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 la, and the radial distribution function is given by this. So we know that radial distribution is given by this. This is no information to us. So they have given you that, and they have told that this is the radial distribution function. Most probably they want you to square and do it, so you don't have to bother about the complex part and the imaginary and the real part. You just simply have to square the most probable distance at which 1s electron, So they have asked the most probable distance, and this is the question. They have not asked for a node. Asking for a node is easy, putting this equal to 0 or putting this square is equal to 0. For most probable radius, you have to differentiate, and you have to differentiate the 4 pi r square psi square graph. You have to differentiate this graph, because that is actually giving you the, you can't differentiate this as has been told in the previous frame. So that is what you have to do. Phi is given, you have to square and differentiate and put it equal to 0 and get the answer. So try to do this one. This was what I was talking about, and hopefully get the answer as one of these. If you get one of these, then you will be getting the right answer, provided you have calculated and got it, not like guessing it. For any axis, Schrodinger wave equation is represented by so they have given a constant of psi is a double derivative of psi is what they have given, some constant and a negative to it. So this kind of thing I've discussed in video number 2 with you guys. The solution can be, we were also doing kind of solutions, right? Like if I differentiate this, if I differentiate that, so what you have to do is you have to work it out. You have to work this part out, differentiate it twice and see whether this plus this is fitting in and giving you a 0 or not. You have to differentiate this twice and see whether this equation is fitting it correctly or fitting in correctly or not. So I hope you'll be able to do these. If you do these, then you have become punters in Schrodinger, what is required for your entrance exams. So best of luck, and I'll discuss the answers in the live class. Bye bye.